Hey guys, welcome back to General Chemistry. Today we're going to apply this idea of enthalpy, and we're going to look at how it is calculated during a chemical reaction. So first we have to talk about the relationship. The enthalpy of a reaction is the amount of energy that is released or absorbed when that reaction takes place. It's going to depend on the differences in enthalpies between the reactants and products. It's also going to depend on the amount of the reactants that we have. So just like we've looked at the coefficients in chemical reactions before, just like we used coefficients when we were looking at stoichiometry of a chemical reaction, enthalpy is also going to depend upon the amount of a reactant that we have. So here we see a chemical reaction. So this is going to be one of our combustion reactions. And what we see here is the chemical reaction is our hydrocarbon reacts with 5 moles of our oxygen to produce 3 moles of carbon dioxide and 4 moles of water. The enthalpy associated with this chemical reaction is negative 2,044 kilojoules. So this negative 2,044 kilojoules is going to be associated with each one of these molecules. So for example, I could say, well, for every 1 molecule of our hydrocarbon that's combusted, it's going to release 2,044 kilojoules. But there's also a relationship between the oxygen as well. So for this one, for every 5 moles of oxygen that break down, we're going to get 2,044 kilojoules released. Now, if I wanted to know how much is released if I do 1 mole of oxygen, I would have to divide that number by 5, right? So this is not the number for 1 mole. This is the number for 5 moles of oxygen. So we're going to have the following equality or the following relationship for our chemical reactions. So we can write the following equality. 1 mole of our hydrocarbon broken down equals 2,044 kilojoules released. Or we could say 5 moles of our oxygen is going to equal the 2,044 kilojoules being released. So what we see here are 2 equalities. This equality is going to get us from units of moles to units of kilojoules. So it's going to go from moles to energy, right? And then it's also going to get us from the stoichiometric coefficients, the 5 moles of oxygen, and it'll allow us to get to 1 mole of oxygen if we want to do that as well. So here is our new equality to get us from moles to kilojoules. So let's see how we would apply this in a problem. So a gas tank in a home barbecue contains 13.2 kilograms of propane, so that's that C3H8. We want to calculate the heat in kilojoules associated with the complete combustion of that propane tank. So we know we have 13.2 kilograms of that propane, and we want to know if I were to burn through that entire keg of propane, how much heat would be released during that process? How much heat could be given off? Okay. So before we dive into this problem, let's just think about the breakdown of, well, what's the path that we would take to solve this? How would we even do that? So just like any unit conversion problem, we're always going to start with the measurement that's given. So we're going to start with 13.2 kilograms of propane. And little twist here, so I'll give you the answer to this one. We don't typically start problems in kilograms. That's kind of a twist for this problem. So the first step is going to be to go from kilograms to grams of C3H8. And we are at the end of our semester, yeah? So we're chemists now. We don't typically deal with the unit of grams. What unit do we typically deal with? Yep, we're chemists. We deal with moles. So that's going to be the next step, is going from grams to moles. And then our last step is we have to find some sort of connection that's going to get us from moles of our propane, so we know how many moles of propane are in that tank, and we want to eventually know, well, how much heat is being released. So to get from moles to kilojoules, we're going to need to jump from moles to kilojoules. And this is where we're going to use that new equality that we saw on the previous slide. Okay. All right, so that's kind of the general path through this problem. Next, we want to go ahead and dive in and get bogged down with the numbers. Okay. So first step is going to be to go from 13.2 kilojoules of my propane to, or excuse me, kilograms, gracious, to grams. Okay, so kilograms cancels, we're left with grams, and there's 1,000 grams per 1 kilogram. So this is going to be 13,200. Okay, and that's grams of propane. So that was step 1. Step 2 is to go from grams to moles. Okay, so to do that, I'm going to take my answer from the first step, start a new train track, and I'm going to do the grams to moles conversion. So grams on the bottom, moles on the top, 1 mole. And to get the grams, we have to go to the periodic table. We add up molar mass of 3 carbons plus the molar mass of 8 hydrogens. So 12.011 times 3 plus 1.008 times 8. And we get the molar mass is 44.097. Multiply across the top, divide by the bottom, so 13,200 divided by 44.097, and we get 299.3, and that is moles of our hydrocarbon. Okay. Now our last step is to go from moles to kilojoules. And we're going to use that new equality that we talked about on the previous slide. So let me get this train track set up. So we start with the answer from the previous step, 299.3 moles. Train track. And moles of C3H8 on the bottom. And on the top, so moles is what we're getting rid of. What's our destination? Our destination is kilojoules, so that's going to go on the top. Okay. So how in the world can we go from moles to kilojoules? Well, it has to do with this it has to do with this equality here. So for every 1 mole of our hydrocarbon that breaks down, it's going to release 2,044 kilojoules. So for every 1 mole of our hydrocarbon that breaks down, it's going to release 2,044 kilojoules. So that equality is stacked one on top of the other as a conversion factor, and now we can multiply across the top, divide by the bottom. So 299.3 times 2,044 negative, and we get negative 61,100 and, oh no, that was not right, 611,769. And the unit for that is kilojoules. So we get 611,769 kilojoules of energy that's being released. How is that energy being released? Well, it's a propane tank on a grill, right? So 611,796 kilojoules of heat is being released. What do we use that heat for? We use it to cook things like our hamburgers and hot dogs, right? So with that heat being released, we could use it to do some work on our hamburgers and cook a hamburger. I hope you guys found this helpful.